Welcome back. So today I'll be talking about a topic that is very popular with you students, that is the Facebook. Uh, this class, we will introduce a collection of topics so that you get the big picture. And then we will go into greater detail into some of these topics. Okay, so the things which you want to just connect together is structure, symmetry, equation of state, and the phase diagram. Okay, so and then we will go in greater detail, especially into these two topics, equation of state and phase diagram. So your textbook starts with the definition of pure substance. I would like to emphasize that this what I would call a pure substance approximation. So I'll clarify what I mean by that. So the textbook defines if the chemical composition is same within the system, it's called a pure. You're calling that system as have it being a pure substance. So it gives some examples. For example, nitrogen. If you have a cylinder of nitrogen, if you have is one component. Air is again has many components, but it is still both these are pure substances, okay, because the chemical composition is the same within the system. However, when you go to this system, for example, the chemical composition here is H2O, and but in the liquid phase, in the vapor phase, the chemical composition is still H2O. So this is a pure substance. However, when you have, let's say, a liquid and it can be water and air, okay, so this is the chemical composition is very different within the container. So this is not a pure substance, but this is still a pure substance because the chemical composition is the same, even though it may have different phases. So this is an all right definition, but when I started thinking about it, I had some reservations. So what I would suggest is, in practice, the pure substance depends on the properties and the processes that we are going to study. For example, if you're looking at gas separation, for example, CO2 separation from an exhaust that is coming out of a power plant, okay, thermal power plant. So that is, by your definition, by the definition of the textbook, that might be considered a pure substance. But if you're going to separate these gases by liquefaction, would you consider that to be pure? I don't think so, because if it's a pure substance, everything would liquefy at a sharp temperature. But if it's an impure substance, the liquefaction at different temperatures, different gases will liquefy. So we have to really look at some greater details when we are defining pure substance. And also, if there are whenever you are considering pure, let's say nitrogen, there is always some impurities that are present in practical application, but in some cases it doesn't matter. And you can take some more examples. So composition, invariably is different at the surface. But if bulk properties are the most important determinant of what we are going to be studying, then the composition impurities at the surface can be neglected. So you have to think deeply into how you're going to be defining this pure substance. Okay, so and then let's say if you are considering radiation thermodynamics, there can be nuclear isotopes. So that might have very different radiation properties. Even though the entire system under study, let's say, you may have chemically uniform composition, but if you're looking at radiation thermodynamics, would you call that a pure substance? So these are some things which you have to think through. We will try to emphasize these points as we go along. So much of when we say chemical composition, we are also thinking about certain kinds of structure. And in this lecture and next few lectures, we'll be trying to correlate structure to properties, thermodynamic properties. So this entire term structure, we can try to go beyond a very descriptive usage. Let's see whether we can define it in more rigorous terms. So let's contrast three different kinds of structure. Here you have structure for solid, you have a structure of liquid, and you have the structure of a gas. So these two are considered fluids, and this is not a fluid, this is a solid. So how do you think about a gas? A gas has very low density, but liquid and solid have higher densities. And a solid has a certain periodic arrangement. Okay, so this is the quintessential description of a structure of a solid, right? There is a periodic arrangement of these solid atoms atoms of the solid. However, if you have a gas and a liquid, they do not have a periodic arrangement. In fact, it is not very clear where would a high density gas compare with a low density liquid. Okay, so these look very similar. It would behave and look very similar. That is a high density gas and a low density liquid. Okay, so are they very different? This is an important consequence we will see in terms of phase diagram. So is there some more fundamental difference between a solid and a fluid? Okay, that's the question we want to elaborate. So can we differentiate the structure in some more fundamental ways? So let's look at that. So before going into that particular question, so we may ask, what is your used to ideal gas from your school times? So what makes a gases ideal? So you say its behavior in terms of at very low pressure and high temperature, right? So that is the ideal gas behavior. What makes it ideal? We say this gas particles do not have any particular structure. They are point particles of zero volume. Not only that, there is no interaction between any two such particles, any two gas particles, there are no interactions. So why is it ideal? Okay, so this ideal properties of gas brings an enormous simplicity in description. Okay, this gas laws, in fact, form the foundation of thermodynamics. There's no reason that such laws should exist. That such simple laws, Charles' law, Boyle's law, all these laws, that they form the foundations of thermodynamics. So that's because of certain ideality in properties that gave rise to properties of gases that gave rise to this simple behavior. In some ways, a solid can also be considered ideal. Okay, so what makes solids ideal? If you ask that question, there is a certain simplicity in description of solid that comes because of one particular fact. Okay, so if you think about gas, there are no interactions. However, other extreme is the solid. There are lots of interaction between each atom of a solid with every other atom of a solid. But despite that, okay, so despite strong energetic interaction, there is a concept of an unit cell, because every atom has a same coordination atmosphere, right? So if I look at one particular atom, let's say this particular atom, it's an atom in the bulk. This particular atom is surrounded by the same chemical environment, and that chemical environment can be replicated in 3 dimensions. Okay, so that is an enormous simplicity, that brings about an enormous simplicity in the description, okay, of a solid, you will see. Okay, so in some ways, gases can be well understood. Ideal solids can also be well understood. In contrast to this, there is nothing called an ideal liquid, okay, because liquids are, you get the worst of two worlds, okay. So in what way? First, you have lot of interaction, just like in a solid, okay, but there are no interactions in a gas, okay. Unfortunately, on top of these lots of interactions, there is no uniformity in the structure around each constituent of a liquid, okay. For example, this, even if you take a liquefied helium, okay, helium is a inert gas. It has been liquefied at high pressure and low temperature. But even liquefied helium won't have any uniform structure. Okay, so this lack of uniformity in structure, okay, is what creates complexity in liquids. So what the take-home message is: there are ideal gases, there are ideal solids, but there are no ideal liquids. Okay, so that makes the study of liquids more complex. So that is these three kinds of this kind of qualitative description. You have seen it from high school. Okay, so you are in an undergraduate program, so your sophistication has increased. So let's see whether we can understand the structure in a more fundamental way. Okay, this is the way the modern science describes structure. So to understand this, we want to connect this structure to symmetry. Okay, so I put it in quotes because I'm going to define what is symmetry. So let's start with asking this question. Which do you think is going to be more symmetric, crystalline solid or a gas? Okay, so you take some time to think about it. So many of you might have guessed that crystalline solid seems to be more symmetric, right? So in fact, in the previous, there is a certain uniformity in chemical structure. So you may, in a solid, so you may claim that crystalline solid is more symmetric. So let's look at this in a more fundamental manner. So here I have an interesting diagram, okay, interesting figure. This is not a gymnast. This gymnast seems to have 3 legs, okay. So what is interesting here? There's a certain symmetry in the structure, right? So how do you, it appeals to you, this word, right? This certain symmetry in structure. What exactly do I mean? So if I rotate this structure around an axis that is perpendicular to the screen, okay, if I rotate this structure by 120 degrees, or by 240 degrees, or by 360 degrees, I would reproduce the same structure. That is, the structure after transformation by 120, 240, or 360 is the same structure that I had before transformation. Okay, so this is in a way the most fundamental definition of symmetry. There is a transformation that is made onto a system under study, onto an object, and you ask the question: how symmetric is the structure after transformation to the structure before transformation? Let's go back to the your original system, 3 systems. Okay, so if I think about a gas, the gas molecules are moving all the time. Okay, they're moving at very high velocities. If I, let's say, measure the density at each point, supposing I have a way to measure density at an atomic resolution. Okay, so the density of in a gas and the density in a liquid, okay, so if at an atomic resolution would be the same. Okay, so throughout this is a container of gas, it's a container of liquid. If I keep my measurement device at each of these points, the density would be the same. Same thing here. The density would be the same all right? So I can translate this system by an infinitesimal change, okay? If I can move the system by an infinitesimal amount, the structure would still be symmetric, okay? So by making this measurement device, if I move this measurement device gradually, I make a transformation. That's what I mean by transformation. By density is the same throughout. So this kind of symmetry, okay, that is, I make a transformation, a linear transformation in my measurement device, and I get the same density. That kind of symmetry in these two systems is called continuous translation symmetry. Okay, that is, I'm translating this measurement device, which is measuring density at an atomic resolution, and I can continuously translate. I would have the same density. That's called continuous translation symmetry. However, when I go to a solid, okay, so what happens? There is high density here. There is no atomic density here. This is an approximation, okay? So approximation Y, okay? So there might be some thermal vibrations which might vibrate, but predominantly this atom is going to be at this point. So when I move this density measuring device, there is high density here, no density here, high density here, no density here, high density here, and so on, okay? So along this direction. High density here, there will be no density here. High density here, no density, high density, okay? So how is this system different from these two systems? In terms of my definition of symmetry, the symmetry of a solid is that this solid has a discrete translation symmetry. So in contrast to a fluid, the fluids had continuous translation symmetry. However, a solid has a discrete translation symmetry. Okay, so that is important to understand these terms. So both have translation symmetry. Okay, but the nature of translation symmetry is different in a solid and from that of a fluid. This has an important consequence in your nature of phase diagrams. Okay, so this is one of the most fundamental way of contrasting why a solid is different from a fluid. You will see a property called critical point. Okay, so the critical point exists because of this fundamental property of fluids having both. Fluids are two things, right? Both liquids and gases have what is called continuous translation symmetry, which is absent in solid. Okay, so I'm jumping the gun here, so we will see. Okay, what do you mean by critical point when we discuss phase diagram, but I'm emphasizing this point because it's of fundamental importance. So if we say in a manner of speaking that this continuous translation symmetry is broken into discrete translation symmetry when you go to solids from fluids. All right, so greater the number of symmetry operations, greater is the symmetry. Okay, so that's the, when I ask this question, which is more symmetric, that's the question I'm trying to answer. Okay, so which system has greater number of symmetry operations? So in fact, if I have a fluid, I have infinite number of symmetry operation. Okay, I can move it by any amount and I will still have a symmetric system. But whereas if I have a solid, I can move by this amount or by this amount and so on, but not by this amount. Then I don't have a symmetric system. Okay, so going by this definition, which is more symmetric, if you pause and ask yourself, even though you may have guessed that the crystalline solid appears to be more symmetric, going by the number of symmetry operation, which is more symmetric. Okay, fluids have greater symmetry because they have greater number of symmetry operations. Okay, so that's an important thing. We'll come back to it when we look at phase diagrams. So the next topic we are going to connect is called the equation of state. So the structure and symmetry determines equation of state. You are used to this equation of state, but even though this term has not been used from your high school, you have seen equation of state. the simplest equation of state is that of an ideal gas law. Okay, so what is an equation of state, for example? So this kind of relationship. Okay, so pressure as a function of, let's say, molar volume and temperature. Okay, that's what an ideal gas law is, right? PV is equal to nRT. N is 1. I have a molar volume. So pressure can be connected to as a function of temperature and molar volume. This is the simplest equation of state. Okay, that brings in an enormous simplicity in description. Okay, so if you didn't have this, an equation of state, all you could have is a gigantic table. Okay, so that is where the pressure is connected to temperature and molar volume. Okay, this gigantic table is eliminated in case of an ideal gas, and you have this ideal gas law. Okay, so this is the ideal gas equation of state. So if I go to a more complex system, more complex in terms of structure, right? So this ideal gas is no structure and no interaction, so to say. So I'll clarify what I mean by interaction. But when I relax this aspect of a system not having structure, I introduce some structure. Okay, so it has some finite measure. Okay, there is some finite size. We are not going to define what do you mean by size. We addressed this issue in assignment 1. It has certain utility, but no precise definition. But still, even with an imprecise definition of size, if I introduce some notion of size, I have what is called the van der Waals equation of state. We'll look into this in great detail, but just to get certain complexity in. So when I introduce certain size, my complexity of equation of state increases. From an ideal gas law, I go to an equation of state, which is called the van der Waals equation of state. So with introduction of some structure, my complexity in equation of state increases. If I go to but still, okay, so ideal gas still has certain symmetry, okay, which still has continuous translation symmetry. My complexity of the equation of state is still less. When I go to a solid, I said that there is a broken symmetry in a solid. The continuous translation symmetry has been broken to discrete translation symmetry. This breaking of symmetry introduces additional complexity and additional material properties too. Okay, so if I look at one of the simplest equation of state in, let's say, in a solid, even in a condensed matter, high pressure, an amorphous liquid, let's say, my pressure as a function of volume is connected to what is called modulus of incompressibility. Okay, so this K and K naught, okay, these are called modulus of incompressibility. We'll define this in some detail, but it's a mechanical property. Okay, so which is yeah, we will define this in some detail in the next lecture or so. Okay, so what is K naught is the modulus of incompressibility at ambient pressure, and so that the complexity of equation of state increases when you go from the ideal gas law, because we have introduced some notions of size and reduced symmetry. Okay, so why do certain systems, okay, have modulus of incompressibility, but certain systems do not have modulus of incompressibility, is because of reduction in symmetry. All right, so this is something you have to understand. Okay, it's a deep point. So let's elaborate on this. The more symmetric a structure is, like that of a fluid, okay, there is more isotropy in properties, material properties. What is isotropy? There's no directional dependence, okay? But solids, for example, if you take diamond and contrast it against graphite, okay? So the diamond is more isotropic than graphite. The graphite, two layers can slide against each other, right? But so the mechanical properties in certain direction for a graphite is very different from its mechanical properties in orthogonal direction, in certain orthogonal direction. So if you want properties to be material properties and thermodynamic properties to be isotropic, the structure, what is underlying the property, the structure has to be isotropic. All right, so this is an important point. So all these things look descriptive. Okay, so can we make it more quantitative? Can we make it more in terms of math? Can we make it quantify? Yes, there is a tool which is called very exhaustive mathematical theory exists. It's called theory of point groups, theory of space groups, which is very important. This gives you a mathematical description of structures, symmetry in structures, and so on. Okay, so you would have to go and take an advanced class to understand this mathematical theory, but it does exist. Don't think it's all qualitative and words. So why are we describing so much about structure, symmetry, and equation of state? Okay, so equation of state is tremendously useful in thermodynamics. Okay, so a good part of this course will appeal to equation of state. We are going to use equation of state to obtain thermodynamic properties, describe thermodynamic processes also. Okay, so equation of state is one of the fundamental things you have to understand to proceed in thermodynamics. So let's move on. So even though we talked about three states of matter from your high school, there was a question in the discussion section also about what about plasmas. Okay, so the plasma is called the fourth equation of state, right? So what do you mean by that? I'm not going to talk about plasmas, just a 1 minute advertisement so that you get interested in plasmas and go and read somewhere. So the way to think about all these things is every system has certain characteristic interaction. For example, there are, let's say, chemical bonding forces between two atoms. Okay, there is certain characteristic quantity. And we also discussed in a previous lecture, temperature is a measure of average energy stored in a degree of freedom, right? So a comparison between this characteristic energetics, okay, the characteristic value of this interaction, energetic interaction between two atoms, let's say it just has certain magnitude, and that is a certain energy scale associated with it, energy value associated with it, and temperature. Temperature is also a measure of energy, right? So heat energy in each degree of freedom, right? So if the comparison between these two is going to determine whether your system is going to be a solid, liquid, or a gas. Okay, so if the temperature is such that, okay, supposing we fix the energy scale, okay, so this energy scale is fixed by, let's say, arrangement in a solid, you quantify the interaction of this particular atom with its surrounding coordination atmosphere. You have fixed that. My temperature is, which is a measure of energy, is low compared to that energy scale, all right? Then I have a solid. Supposing my temperature is much higher compared to the energy of interaction of that particular atom with the surrounding coordination atmosphere, then I have a gas. But if my temperature is comparable, okay, to that interaction, I have a liquid. Okay, so that's the way I have to think. Okay, so again, let's go with this. I have an energetic scale. Okay, so let's say this interaction is, let's say, epsilon, and my coordination has, let's say, 8 coordination. Now, the coordination number for each atom is about 8, let's say. So each interaction is 8 epsilon, right? In energy units. And then if that interaction is much higher, that's than the temperature, okay, at hand, okay, so the temperature of the system, okay, then it will be a solid. But if the temperature, which is a measure of energy, is much higher than 8 epsilon, all right, then you will have a gas. But the temperature is approximately equal to 8 epsilon, then you have a liquid. Okay, so if there are more questions on this, of course, we can take it up in the discussion hour. So compared to all these things, what is a plasma? So plasma is way above this, all right? So even this fundamental integrity of an atom here, okay, is lost. Okay, so in sun, you have plasma, let's say hydrogen plasma, helium plasma, that is even helium atom is ionized. Okay, so you just have a soup of charges. What is the soup? This soup is made up of electrons and ionized nucleus. Okay, so that state of matter, it has its own equation of state, properties which are very fundamental. Even though we're not going to be studying that here, it's very fundamental. That can be well studied. It's important for many things, climate, cosmology, and so on. Nuclear energy processes, nuclear fission, fusion, especially fusion. It's very important to understand these things. So it's of great consequence, but we are not going to be addressing that in our in this course, but at least you should be aware of what you mean by plasma. So the temperature we are thinking about when we are discussing, if we discuss plasmas, is way higher compared to any of the temperatures we'll be using for describing these particular three systems. So all this looks fine, but when you try to, one of the complexities with thermodynamics is when you try to apply it in practice, it's not at all trivial. Okay, so so I want to once in a while take you at least give you a view of complexities that arise when you try to apply thermodynamics in engineering practice and science practice. So actually the structure which we have to deal with is multi-scale, okay? So one of the important structure that is of enormous importance in engineering application is microstructure, okay? So for example, from high school, you're aware of atomic structure. You're also aware of crystal structure from high school, at least in a qualitative, descriptive manner. There's also magnetic structure, ferromagnetic structures, and so on. So it's all electromagnetic in origin. These are all have certain symmetry. Okay, there is certain periodicity here. Okay, that simplifies your description. Okay, so but the real engineering systems are way more complex because the real engineering systems are made by a complex material processing techniques. Okay, so these involve high temperature, non-equilibrium processing. High temperature, sometimes you impose certain stresses. So this thermomechanical processing introduces a lot of complexities, and these are very important. You should be at least aware of that. These are called microstructures. That is the sum of three things, have certain unique phases, defects, vacancies, or missing atoms. Okay, in these structures, if there is some atoms that are missing, they are called vacancies. That's a defect. Then there are some other more complex defects called grain boundaries. And because of this thermomechanical processing, there are residual stresses. Okay, all these things make practice of thermodynamics to real systems more complex. How do you define phases here? Okay, what are the degrees of freedom? All these things are complex. Okay, so we will try to touch upon this so that you're not at a loss. Okay, I learned all these things in my ESO thermodynamics class. How do I, when I start looking at the system, suddenly you should not be at loss. So we'll at least give you an idea on how to go and where to go and look at these additional complexities in thermodynamics. So, but what you should understand is there is multiple scale. There is fundamental particle structure. We won't be addressing that at all. There is nuclear structure, which is important, at least in nuclear engineering and mechanical engineering and some aspects of materials engineering too. And then there is atomic structure. It's going to be increasingly important to this subject, electronic structure. And then there's crystalline structure. And then there is microstructure, all right? So which structure is important, okay? That depends upon application under consideration, right? So we will look at these complexities. So greater structure, more richer the structure, more complex is your equation of state, and then the more complex is the phase diagram. So what do you mean by phase diagram? These kinds of things, which we'll be drawing a lot. Okay, so on one axis there'll be pressure, on the other axis there'll be molar volumes. As you vary pressure and molar volumes, which phase exists? This is all phase diagram for a pure substance. Okay, both these things are phase diagrams for pure substances. Whether at that pressure and molar volume, or at that pressure and temperature, or temperature and molar volume, do we have a gas or a mixture of liquid and vapor or a solid? Okay, this kind of description, this kind of diagrams are called phase diagram. We look at it in great detail. This is going to be very important in applications like refrigeration and so on. Very important. So we look at it, but it's just insight into just a brief view, okay, to in phase diagrams, so that all these things are connected, right? So structure, symmetry, equation of state, and phase diagram. Right? So I already connected how structure and symmetry is connected to equation of state. And the equation of state, the mathematical complexities in the equation of state is going to determine your phase diagram. So this is all for pure substance. Even in pure substances, the phase diagram can get complex. And as you introduce from a pure substance, you introduce chemical complexity, the complexity of the phase diagram increases. Okay, so this what I would call the second most important phase diagram in human civilization. Okay, so human civilization has a lot to do with steel. Okay, steel is not one particular thing. This phase diagram, or what is called the iron carbon phase diagram, it's an extremely important thing in human civilization itself. You are plotting temperature in the y-axis, here carbon content in the x-axis. Okay, the amount of carbon is not lot. Okay, so that introduces an enormous complexity, richness in properties of steel. Okay, so the utility of steel is so different depending upon the way it's processed. Okay, the way the phases are distributed, the chemical composition, and so on is very important. At least you should be aware of this particular phase diagram. And I'm mentioning this is the second most important phase diagram. So what do you think is the most important phase diagram in whole of human civilization? Okay, so that is a question for you to think about. So while we'll look at what is the most important phase diagram in human civilization. With these thoughts, I would end here.